Hey, what's up? I'm Eric here. Today's project is making walkie-talkie. The walkie-talkie has a half-duplex communication. If one side is speaking, the other side should just listen. Connecting to devices with Wi-Fi and transfer data via WebSocket. In this video, the focus is on implementing a half-duplex approach. Okay, let's get started. The first thing to do is to have wiring. Yeah, I know, but I had to do it. There is no specific GPIO pins for the I2S interface, so you can do whatever you want. As you can see on the screen below, I have arranged both the MAX 983578 for outputting speaker and the INMP441, which is the I2S MEMS microphone. In the previous video, the basic explanation of MAX 983578 and INMP441 was given, so please refer to it if necessary. In this project, I prepared two identical devices. One becomes a server and the other becomes a client. Also, both devices have the same wiring. There is nothing special in it, so let's move on quickly. It's not fun to do wiring only on a breadboard, so I made it the same with the blank PCB. Of course, this is an unnecessary task. I just made it for fun. It looks not good because it's roughly made without thinking carefully. Anyway, this is not a point. Let's move faster. It's done. I'd like to make it something similar to the walkie-talkie, but totally not. And for your information, the reason I use the TTGO model is that it has a built-in display and a button. So it's easy to use, right? If you don't have this model, there is no problem with adding only a button to the ESP32 dev kit. Time to move to the software part. I'm using Arduino IDE 2.0 beta version. It's much lighter than the existing Arduino program and is convenient to have multiple projects at the same time. This is especially good for debugging servers and clients at once. So I recommend you try this one for your next project. Here's your source code. As you can see, there is a code for the server on the left and a code for the client on the right. This code can be downloaded via the link below. One thing I should say is that this code was originally able to select the role of the server or client in one code. However, the problem is that it's too illegible and difficult to explain the code, so I separated the server and the client side. So most of the source code are the same. Of course, there are different parts of the code because it works differently depending on the role. The first part to see is the const header file. Here, I have defined the roles required for the system. Each shows a predefined server and client. In addition, there are parts to indicate the state of the system. To ensure this, three states have been defined that represent each state. It's idle, speaking, and listening. You can switch the state to speaking or listening in idle, but you can only go to idle in speaking and listening. This plays an important role in maintaining the current system. Also programmed to proceed according to these rules. The next is the I2S setting part. The I2S setting header contains everything about sound input and output. Output sound to a TX port, receive microphone input to RX port. The sampling rate is 16 kHz, the bit depth is 32 bits, and the buffer is 1024 bytes at a time. When speaking mode starts, it will install RX port and uninstall when finished. Also, when the receiving mode is started, the TX port will be installed and uninstalled when finished. This is also 100% same code for both a server and client. This font header is for easy use of the default fonts provided by TFT ESPI. Here's the main code. In fact, the code itself is not that long. What we need to understand is not the code, but the way the whole system works. Let's first look at the basic communication structure. Here is a slide I prepared. The server first starts Wi-Fi AP mode and also WebSocket server. The client tries to connect the access point on the server and WebSocket also connects. When a client connects, the first thing the server does sends its own timestamp to the client so that it has the same timestamp as the server's one. It does not synchronize the actual timestamp. it simply keeps the difference calculated. It's important because it's used to change the state with the timestamp. Here's one more thing. Clients connected to the server must continue to take certain actions to see if they are still alive. When the client is idle, it sends a dummy value once a second to server to notify that it's alive. Let me go back to the code. There are two buttons on the TTGO, but only the right button is being used. It's only using pressed and released events, and the pressed event is the starting point of the communication. It's similar to how it works with Walkie-Talkie. Pressing the button on the sending side occupies the line and transmits voice data. One thing we need to take care of is this system is in a server-client relationship. It means the client requires permission from the server before any action can begin. In this section, the code for the server and client is different. Let's see how the client can get started first. When a button is pressed from the client side, a synchronized timestamp is sent to the server. If the server is idle, it sends the timestamp back to the client. This is a kind of permission to let the client transmit the audio data. The client becomes the speaking mode and starts sending binary data to the server. The server is already in listening mode, so the incoming data is already ready to be written to the I2S. When the client releases the button, it sends timestamp again to notify the end of the transmission, and then returns to the idle state. This is how clients send data. The server side is much simpler. The server itself is a commanding authority, so it doesn't need to ask permission. If its current state is idle, it can forward the audio data immediately to the connected client. When the server sends the current timestamp, the client compares it with the timestamp of the client's own last action. If the two are different, it means the server is trying to send data because it belongs to the server, not to itself. The server sends audio data, and the client writes the incoming bytes to the connected I2S TX. When the server releases the button, a timestamp is sent again, and both returns to the idle state. This is how half-duplex communication is implemented based on the WebSocket. If you look at the code again, it's all I have explained so far. If you have any questions about this code, please leave a comment below this video. I will show you how the two devices will actually work. The client is on the left and the server is on the right. As soon as the power is turned on, it's connected via Wi-Fi and up to the WebSocket. When I press the button on the server, speaking mode starts and the client starts listening mode. As soon as I release the button, you can see that it returns to idle mode on both sides. The client is the same. Pressing the button in idle state turns the speaking mode, and releasing it returns to idle mode. The feedback sound is being heard because the two devices are too close now. You have to keep some distance for the test.